10.2-2, we are doing, so we are still within the comparing two means. So this will be part 3, I guess. Is it part 3? Part 2, right? Part 2, right? We only need one, right? We only need one, right? So this is the second one, right? So comparing two means, part 2. We are on page 655, where it says significance tests for mu1 minus mu2. So, I mean, the same thing as before, right? We're going to do, the whole is going to be mu1 minus mu2 is equal to 0. The how is going to be mu1 minus mu2 is not equal to 0 with an alpha of whatever it may be, right? And then we're going to go, right? This is the significant testing. So on the, this is the state. So the state we will be doing a 2-samp T test, right? 2-samp T test, and we will be doing this. And then in the planned state, we would do what? We would check for our conditions, which are exactly the same as our confidence intervals, right? So we would check for random sample. Right, we can't oversample, right? And then we would have the large counts. The large counts would be what? What am I checking for? Huh? Greater than 30, right? And greater than 30, right? If they were a normal population, it doesn't matter, right? If it's normal, it doesn't really matter whether it's greater than or less than, right? If we do not know, and it's less than 30, then we have to do a dot plot to see if it's roughly symmetric and no outliers, right? For 656 on the top has those conditions one more time, right? The data come from 2 independent randoms, okay, less than 10%. For each sample, the corresponding population distribution is normal, or the sample size is greater than 30. Right? If they're normal, if they're less than, but I know that they're normal, I'm still okay. Right? Okay, for each sample, if the population is unknown shape and n is less than 30, then you would have to do a dot plot, histogram, similarly plot, whatever you want, right? Okay, so let's go ahead and do the example there. A longer work week. A longer work week. Has the mean number of hours Americans work in a week changed? One of the questions in the general social survey asked respondents how many hours they work each week. Responses from random samples of employed Americans were recorded for 1975 and 2014. And they were summarized as here. So 2075, we sampled 764 people, and there was a mean and a standard deviation. Same thing with 2014. Okay. Do these data give convincing evidence at the alpha equals 0.05 significance level of a difference in the true mean numbers of work hours per week? Okay. So, and A, state the appropriate hypothesis and performance and whatever. So 2-samp T tests, the whole would be what? For 1975 and 2014, right? 1975, 2014. All right, that's what we're doing. Right? We're checking to see the difference here, right? At an alpha of this level. So that's that. And B, check if the conditions for performing the test are met. It's a random sample. It says it's a random sample. And the population was what? Population were Americans who worked, I guess, right? What to say? Mean numbers of hours of Americans working. They surveyed what? Random samples of employed Americans. Employed Americans. So we're going to assume that there are a lot of Americans that were employed during that time, like millions and millions. So the N size is going to be less than 10%, right? N1 is 764 and N2 is 1501 there. Okay, so that's that. And so that is good. And what about the large counts? N1 and N2 are both greater than 30. Right? So it doesn't have to be normal, although we expect it would be normal, right? Does anybody remember where the 30 comes from? The central limit theorem, correct? Central limit theorem. Okay, all right. Okay, so we're good with that. So how would you calculate the standardized test statistics and the p-value? Okay, the T star there. The T star is going to be equal to, that's on page 657. We're going to have x1 bar minus x2 bar. This is what we're looking at, and we're going to subtract that from 0, see if it's 0, right? And then we're going to have the standard deviations, right? So we're going to know the standard deviations. Standard deviation of 1 n1 squared plus standard deviation of 2 squared over n2. Right? We're going to use that. And this is how we would calculate the T star. Right? And then obviously there's a calculator method. All right, so let's continue on and see if we can go ahead and make this work. Example referred to the previous one, and we're using the same things here. Okay, we already confirmed the conditions for performing the test. A, explain why the sample results give some evidence for the HOM. Well, this mean and this mean are different, right? That's our some evidence, right? We have some evidence that they're not the same. Because one is 38.97, the other one is 41.91. Okay. B, calculate the standardized test statistic and the p-value. So it looks like, oh, let's take the book, switch these. So I'm going to switch them also. So we're going to say that 2014, 2014, 1975, 1975. So we're going to have here, what we're going to have is 41 point, what was it? 41.91 minus 38.97. 97. And then we're going to have a standard deviation for 41.91 was, standard deviation was 14.35 squared over N2, which was 1501. And then we're going to have 751 over, what was the standard deviation? 13.13 squared. Was it 751? Was I correct in 750? Oh, not even close. 764. 764. 764. If you do that, you are going to get 4.88. 4.88. Okay, so that is the T star. Okay, so what are we going to use for N? What do we use for degree of freedom? Remember we said there N1 and N2 are different. Which one are we going to use? We use a smaller one. We have to use a smaller, we have to be more conservative, right? So the degree of freedom is going to be what? 763, right? 763. The problem is, go to the back of your book. I guarantee you there is no 763. Where are we at? Chi-square. All right, here. So we're on T-3. Yeah, we have 100 and 1,000. So which one are you going to use? Use 100, right? Use 100 there, and we are at 95%. So what is it? 1.984. Is that what we're getting? 1.984. What is the book at 1.94? Did you get 1.94? Oh, they just went ahead and do the T-SAM test. Never mind. Oh, 4.88. I'm sorry. So 4.88, right? So we have to find out where it's, where we at? We're way out the other side, correct? So at 100, it's going to be what? Where are we at? 0.0005 times 2, 0.0005 times 2. So where is that p-value there? Where do you find the 0.0005 there? You're at 100 and we are out there, so it's like the very end. Can you see at the 100 row, we're at 3.39, right? You see the 3.39? It's at the 0.0005, right? And we're past that, right? Because it's 4.88. We're 4.88, right? So we're going to call it at most 0.0005. Multiply that by 2, because that's on one side and one tail. 2 tails, so it's going to be 0.001 at best. 0.001. The p-value is 0.001. So therefore, the p-value is what? Less than or greater than the alpha. What was our alpha? Alpha was 5, and we're at 0.1. So the p-value is less than the alpha. Therefore, we reject the hope. We have convincing evidence that the high is correct. Okay, so that's that. And we're good. So let's go ahead and do that one more time. Let's do the calcium and blood pressure. So I'm going to have you guys do that. And I want you guys to use your calculator doing the 2-stamp t-test using that. You can do that. notice on this one, our n is gonna be small, right? Our n's are gonna be small there, so you're gonna have to do the dot plots there. The book was so kind to do for you. Nonetheless, you have to realize that, you know, on a task that you would have had to do. So I understand that it would have been better for us to have done this before you took the test in chapter 9. Was everybody able to figure that out? Did everybody get that? Are we good? We're able to do the two-samp t-test. Okay, so there's two-samp t-test, there's a two-samp t-interval, and there's a two-prop z-test, two-prop z-interval. Okay, all right, you guys need to know all these things while you're doing it. Okay, we're good. And the very end on page 663, there's a little blurb there about pooled data. Pooled, you guys, somebody asked about that pooled, I just said just not use it, right? I mean that comment, okay. Pooled data is when you make the assumption that the standard deviation of N1 and N2 are the same. If you make that assumption, you can go ahead and derive a different expression for this guy down here. Okay. But we're not going to do it. So I'm just, if you want to read it, go for it, go ahead. It's interesting reading. So if anybody asks about pooled data, say that it could only use when the standard deviations are the same, which is very rare, right? And then we just don't use it. Okay, that's all you really need to know about it. All right, we're done.